In the end, yes, everybody can say we're all Ethiopians, we're all Africans. That's like, no doubt, nobody doubts that. None of these countries have that complete record like Ethiopia has. And they can't really say that we have fossil remains of 13 species from the past. Every human being that lives on every corner of the world, they trace their origins to Africa. If you want to be specific, then of course they trace their origins back to Ethiopia.
Let me come to you. I know you have a project here in Ethiopia, and your collaborative efforts are, shedding spotlight on some of amazing discoveries, including the relationship amongst the earliest Australopithecus species and the evolution of numerous extinct and extinct mammalian taxa. Could you please explain that in simple terms so that we'll understand it in a better way?
So, as paleoanthropologists, when we go out to the field, to places like the Afar region or to the Omo Basin, we always have one thing in mind, which is find the remains of the earliest human ancestors, because that's really what we want to reconstruct. Where did we come from, right? But at the same time, finding just the hominin fossils is not going to give you a lot of information, because we know that in the past, like today, humans live together with other animals, right? There's so many kinds of animals that live around us, okay? So did they in the past. So they die, and they fossilize like the early human ancestor fossils, individuals. So when we collect these fossils, we collect everything. We collect the fossils of antelopes, we collect the fossils of elephants, rhinos, all kinds of animals that we can find, even aquatic animals like fish, turtles, and crocodiles, and so many others. Now, why do we collect all this, right? If we're interested in understanding human origins and we're interested in recovering fossil remains of early human ancestors, why are we collecting all these other fossils of other animals, non-human animals, right? So, in order to understand these early human ancestors, how they lived, in what kind of environment they lived, if we want to understand that, we need to understand their environment. Who are they living with? Because most of the information about the environment, their environment, comes from the animals that were living with them. Because some of them have very specific habitats that they live in. And we try to understand their diet, what kind of food they were eating, how they were moving. All of this gives us information about, like, for example, Lucy. Lucy's species Australopithecus afarensis lived like 3.2 to 3.8 million years ago, right? In what kind of environment was it living? We can't really answer that question by just looking at the fossils of these early human ancestors. We have to look at all the fossils that have been recovered representing other animals. And by studying those animals, we now know that Lucy's species Australopithecus afarensis lived in a variety of habitats. It was not specifically living in a forested habitat. It was not living in open grassland. It was not, specific to any habitat. All of that information comes from studying the fossils of the animals that lived with her. So at every step in the past, when we study human origins, when you study or look for fossils of early human ancestors, you also look for fossils of other animals, because those are what give you the information about the ancient habitats and the environment in which these early human ancestors lived. So basically, when we have early human ancestors that are like from different time periods, we always try to understand, like, how is this earlier hominin or human ancestor related to the one that came after that? When did the transition happen, if it was a transition? And we try to trace all these evolutionary processes through time. And every time we see changes, let's say, for example, Lucy walked on two legs. And by the time she was discovered in 1974, the earliest human ancestor fossils that we had were younger than 3 million years. So people thought that bipedality, meaning walking on two legs, started younger than 3 million years. But when Lucy and her relatives were found, and they were dated older than 3 million years, she became the oldest human ancestor known. And she walked on two legs. But she still had a very tiny brain. Her brain size was very small. So when we think about humans, we have big brain. We walk on two legs. So we expected to see bigger brain, walking on two legs, but that's not what we saw. So the brain expansion came very late in our evolutionary history. So you look at this human ancestors like Homo erectus, 1.6, 1.5 million years ago, they have already increased the size of their brain. They've become bigger, right? And they're still walking on two legs. So basically, why is this brain increasing in size after Lucy? Okay? And it's really connected to the beginning of our own genus, Homo. And what was so special about Homo, right? Well, because Homo was the first one to actually make tools and use tools. So that technology literally changed the way this early human ancestor lived, because having tool means you have access to meat. You can cut meat from animals. Meat, fat, that's basically what makes your brain larger, right? So there is causality in terms of why there is an increase in brain capacity from time to time. And it didn't stop. Once Homo erectus started using tools, not only were the tools being, modified to be better, but their brain size was also increasing until we got to ourselves. Now we have a brain capacity of maybe about 1,300 cc, which is big brain relative to our body size, right? If you go back 200,000 years, 300,000 years, it's just a little smaller. You go back in time, it gets smaller and smaller.
It's a gradual process.
Gradual process. So the reason why we would like to understand all of this process is because who we are today and how we got to be here today, what evolutionary processes have we passed? That's what we're trying to understand.
Right.
The place being one thing, where are we evolving and where are we finding these fossil specimens? The key thing for us is to understand the evolutionary processes that took place and when changes happened and why did they happen. A simple explanation that I was trying to explain was, why did we start having big brain? What changed? Stone tool technology, having stone tools, having access to new food resources like meat.
Right.
Those changed our evolutionary course in a different direction.
Yes.
Our brain started expanding.
Wow. Yeah.
And just think about today. Technologically, today, where are we? For Homo erectus, a simple cutting tool was a huge breakthrough. It was a big technology, right? So that's how we see our evolutionary history. From time to time, we've been changing a lot of things, both biologically and culturally and archaeologically.
When we study the age of the specimen, I think carbon dating is very important. What exactly is carbon dating? Could you please explain that to us?
A lot of people know carbon dating because it's been around for hundreds of years, right? But the only problem is carbon dating is not something that we use to date ancient fossils. You cannot use carbon-14 to date anything that's older than 70,000 years. So when we're talking about millions of years, there's no way you can use carbon-14 dating method. So the way it works, to answer your question, is so minerals, this is a little bit scientific. So minerals have different kinds of elements. One is radioactive and the other one is stable. So the radioactive kind of through time decays into the stable form.
Okay.
And we have something called half-life, which means for however many radioactive elements there are, for half of them to become stable, there is a set time in terms of how much time it takes. So for carbon, it's 5,730 years, like the half-life. So basically, you don't have enough time for the whole thing to actually decay into the stable form. That's why it has a very short limit in terms of how far you can use it. But for ancient fossils like Lucy, for example, or Ardipithecus, we use a different technique of dating. Okay, because dating is really important. Unless you know how old these fossils are, you can't really reconstruct your evolutionary history because you don't know exactly what happened when, right? So time is really significant in terms of interpreting how we evolved to who we are today. So geologists, this is the work of geologists mostly, they go out to the field with us. And we paleontologists hunt for fossils.
All right.
The geologists actually hunt for volcanogenic rocks, rocks that have minerals that are shiny, that can be sampled, and those are the rocks that they date. They bring them back to the laboratory. We don't have the laboratories here, but they export them outside where they have mass spectrometer and other machineries. And basically, the methodology is the same, meaning they're looking at decay process, radioactive elements decaying to their stable forms, but some minerals have a very long half-life. So you can use those methods to even date the oldest rocks on the face of the earth. We're talking about billions of years, right?
Oh, yeah.
So in our case, once it's older than 70,000 years, because we cannot use carbon-14, we use other methods called argon-argon method, potential-argon method, and there are also other kinds of dating methods, but the methodology is similar. It's just based on decay of radioactive elements to their stable form. So people wonder how do you date a 4 million year old human ancestor? Well, that's a very good question because people have been used to carbon-14, as you mentioned earlier, but that's not what we use. What we use is we don't date the fossils themselves, directly, because there is nothing that we can get from the fossils themselves to date like carbon-14. Because carbon-14 basically you take sample from the bones themselves, because it's organic. Carbon is organic. Everything is built off of carbon, right? So you can sample that carbon from a living tissue, basically. But once you get to the millions of years, all the specimens that you're seeing, they are all replaced with minerals. There is no organic material in them. It's just like a rock. They just kept the shape of that specimen, right? So what that means is you can't really date them, directly. So what we do is, that's why for older deposits, it's always good to have volcanogenic rocks that could be dated above and below the fossils that you find. So usually when we give age estimates for fossils older than 100,000 years, we say they are between this and that. We give 2 ages. Simple example, Ardipithecus ramidus. It was found between 2 volcanic horizons. And the geologists dated those 2 volcanic horizons, and they will tell you the minimum age is what is on top, the maximum age is what's below it. So it's a bracketing age that they give you.
It's kind of, they give you this range.
Exactly, it's a range. So that's the range you get for all the older specimens. But sometimes you could actually be lucky that the deposition time is really short. In the case, I brought Ardipithecus ramidus because that's the best example of how short the gap was between those 2 dated tuffs. We're talking about 4.4 million years ago, right? And the volcanic rocks that we had from above and below the specimen actually gave almost similar age. The difference between them was 50,000 years. And for a fossil that's 4.4 million years old, 50,000 years is nothing. It's one day. So basically, if you're lucky, you can get those kinds of dates. But for most of the time, people will give you, this fossil was dated to between X and Y. So it's like a range that you have. So in between those will be the age of the fossil.
All right.
So there are also other methods to refine further, how old that fossil is, depending on what we call deposition rate. And we can calculate that and get it closer to what the age of that fossil could be.
What's the benefit for Ethiopia being the origin of humanity? How is it, properly making the best out of this?
Well, there are so many ways to answer this question. I think the fact that Ethiopia is the real cradle of humanity has attracted so many scientists from all over the world. And these scientists come to Ethiopia to study these fossils. They come to Ethiopia to look for the fossils by going out to the field. So from a scientific perspective, Ethiopia is providing science the best evidence that you could get on the origin of humanity. That is from the scientific perspective. Now, countries who have fossils, like South Africa, for example, I mean that's the best example you can have when it comes to like how fossils in a country have actually been used to actually promote tourism in that country, right? So South Africa, when they found the first early human ancestor fossil in 1924, they kept finding more fossils from cave sites that they have in the 1930s and 1940s. This is when no early human ancestor fossil was known from Eastern Africa. Kenya, Tanzania, we don't have anything. Ethiopia, nothing, right? So basically, South Africa claimed itself to be the cradle of humankind. And at that time, indeed, it was, because that was the only place that we have the earliest human ancestors. Who knew that, like 50 years later, sites like Hara were going to be found and provide like even older hominids, right? So what they did was they trademarked the cradle of humankind. It's a trademarked saying, like phrase, the cradle of humankind, kind of which means, exactly, which means you can't use it. So South Africa did like this sites where we have all these cave sites. It was approved by UNESCO to be World Heritage Site. Like, this is the origin of mankind, okay? And that attracted a lot of tourists to the country to see it, okay? Now, when all these fossils are found from Ethiopia and from other places like Kenya and Tanzania, of course we know from a scientific perspective that South Africa is not the cradle of humankind, because we have older, ancient human ancestors from Ethiopia, right? But basically, have we used it to promote that recognition as much as South Africa did, right? That's the big question. When we talk about like tourism, that's something that we have to really think of. How can we promote Ethiopia as the real cradle of humanity so that the world knows not just Lucy, because Lucy is like the most iconic specimen that you can imagine. Every corner of the world you go, they know Lucy. But they don't connect that to Ethiopia being the true cradle of humanity. So what we need to do is to connect those, that Ethiopia is not only the land of Lucy, but also the land of humankind. This is where human ancestor originated. So basically, we can use that as a promotion to attract a lot of tourists to actually visit their country of origin. Yes. Basically, that's the reality. It's their country of origin. But I don't think we have done enough, like countries like South Africa, who used whatever fossils they have to promote their country as the cradle of humankind. And I think it's doable. It's just about how we promote what we have in the right way, because we haven't done that yet. Yeah. We have promoted individual specimens like Lucy, like Selam, but we haven't introduced Ethiopia as the cradle of humanity. We know it is, but are we talking about it out loud? Have we said it widely to the world, right? And I think that's what's missing right now. Yes. And that's something that we have to really think as a country. I think we need to promote Ethiopia as the true cradle of humanity and make it heard by the whole world, right? Yes. If we can do that, I think we would do better than South Africa in terms of being recognized as the true cradle of humanity.
Yes, Professor, I think that's the assignment that's going to be done by everyone concerned. Thank you so much for giving me this wonderful interview. Thanks a lot.
Thank you so much for having me. This is very exciting to share human origins stories.
Definitely. Well, dear viewers, with that, we come to the end of today's program. Thank you as well for having been with us so far. Until I see you next time with yet another program, it's a bye-bye from me. Shfaralak.